Box office revenue prediction using linear regression. In this lesson, you will learn how to predict movie box office revenue using machine learning. Predicting revenue can help movie studios, investors, and data scientists make smarter decisions. You will explore, visualize, clean, and model movie data step by step. No prior experience is needed. We will explain every concept in plain language. Let us get started and have fun learning data mining for real-world business questions. Running the cell now. What is linear regression? Linear regression is a simple way to predict a number based on past patterns in data. In this lesson, our goal is to predict box office revenue for movies. We use past data about movies like budget and popularity as input features. The model learns from examples to estimate the revenue of future movies. This is a supervised machine learning method. The model sees both the answers and the inputs during training. You will see how it works with real data and code. Running the cell now. We will start by turning off warnings in our notebook. Suppressing warnings makes our outputs easy to read and less distracting for beginners. #suppress warnings for a clean notebook. Import warnings, warnings.filter warnings, ignore. Import numpy as np. We set the random seed to 42 for reproducibility. Running the cell now. Here, we set a random seed to ensure consistent results when training our linear regression model. This step doesn't produce visible output but is important for reproducibility, meaning each time we run the code, the data and model behave the same way. This consistency helps us reliably evaluate how well our model predicts movie box office revenue. Now, any warning messages will be hidden, so you can focus on learning. You can add this at the start of any new Jupyter project when you want to keep things tidy. Let us start by loading the TMDB movie box office dataset. This dataset includes data for thousands of movies, including features like budget, popularity, and revenue. We will use pandas to handle data, KaggleHub to fetch from Kaggle, and look at the basic shape to check the load. #data setup. Import KaggleHub, OS, pandas as PD. Path equals KaggleHub.dataset_download, TMDB, TMDB movie metadata. Files equals os.listdir, path. df equals pd read_csv, os.path.join, path, tmdb_5000_movies.csv. Print, df.shape. Print, df.head, 3. Running the cell now. This output shows that our movie dataset contains 4,803 rows and 20 columns, including key features like budget, genres, popularity, and original title. Notice the variety of data types, from numerical columns like budget and popularity to text and nested JSON in genres, which will influence how we prepare the data for linear regression. This step confirms we have enough diverse movie examples to train a model predicting box office revenue based on past patterns. You can see the number of rows and columns in our dataset and a preview of the first few movies. Each row is a movie, and each column gives information about the movie such as budget and revenue. We will use this data to build our box office prediction model. Before working with data, it helps to understand its structure and get a quick overview. We use the info method to see columns, types, and missing values. #explore basic data info. df.info. Running the cell now. This output shows the structure of our movie dataset with 4,803 entries and 20 columns, including key features like budget, popularity, and revenue. Notice some columns have missing values, which we'll need to consider before training our linear regression model. Understanding these details helps us prepare the data properly to predict box office revenue accurately. This tells us how many movies we have, which columns are numbers or text, and where we might have missing data. Later, you will see why identifying missing values now is important for cleaning. Next, Let us check all the column names in the dataset. We also look at basic statistics like the mean, minimum, and maximum values with the describe method. #C column names and sample statistics. Print df.columns.tolist. Print df.describe. Running the cell now. Here we inspect the dataset columns and summary statistics to understand the movie data's structure and key numerical features like budget, popularity, and revenue. Notice the wide range and variation in these columns, especially revenue, highlighting the complexity the linear regression model will address. This step sets the foundation by revealing what data we'll use to predict box office revenue. Looking at statistics helps us understand which columns might be useful for predicting revenue. For example, the budget and popularity columns may be good predictors. Before modeling, we must handle any missing or blank data. Let us see if any of the most important columns like budget, revenue, or popularity have missing values. #check for missing values in important columns. Print df, budget, revenue, popularity.isnal.sum. Running the cell now. This output shows that there are no missing values in the key columns, budget, revenue, and popularity, meaning our dataset is complete for these features. This is important because linear regression models require complete data to learn accurate relationships and make reliable predictions about box office revenue. If you see any non-zero numbers, it means some movies do not have those values filled in. We need to fill in or remove those missing data points before training a model. Movies with missing or zero budget or revenue values are not helpful for our prediction task. Let us remove those rows so our model learns from complete real examples. #remove rows where revenue or budget is 0. df equals df, df, budget, 0, and df, revenue, 0. df equals df.dropner, subset sad smiley budget, revenue, popularity. Print df.shape. Running the cell now. This output shows that after removing movies with zero budget or revenue, and any missing values in key columns, 3,229 movies remain in the dataset. Notice the reduced number of rows ensures the model trains only on complete, meaningful data, which improves the accuracy of predicting box office revenue. This cleaning step is essential before fitting a reliable linear regression model. Now our dataset only contains movies with proper budget, revenue, and popularity data. This helps the model learn from real numbers and avoids confusion. Let us visualize the connection between movie budget and revenue using a scatter plot. Looking for patterns visually helps you see if higher budgets usually lead to higher earnings. #check basic relationship between budget and revenue using a scatter plot. Import matplotlib.pyplot as plt. plt.figure, fig size sad smiley 7 4. plt.scatter, df, budget, df, revenue, alpha equals 0.3. plt.xlabel, budget. plt.ilabel, revenue. plt.title, movie budget versus revenue. plt.show. Running the cell now. This scatter plot shows the relationship between movie budgets and their revenues, with each point representing a movie. Notice the general upward trend, indicating that higher budgets often correspond to higher revenues, which suggests budget is a useful feature for predicting revenue. This visual insight motivates using linear regression to model and quantify this pattern. You will notice that movies with larger budgets often earn more in revenue, but there are many exceptions. This kind of plot helps confirm that budget is an important feature for predicting box office results. Popularity in the dataset is a score reflecting public interest in a movie. Let us plot popularity against revenue to see if more popular movies tend to earn more. Visualize popularity as a feature. plt.figure, fig size sad smiley 7 4. plt.scatter, df, popularity, df, revenue, alpha equals 0.3, color equals a green. plt.xlabel, popularity score. plt.ilabel, revenue. plt.title, popularity versus revenue. plt.show. Running the cell now. This scatter plot shows the relationship between a movie's popularity score and its box office revenue. Notice the upward trend, suggesting that higher popularity often corresponds to higher revenue, supporting the idea that popularity is a useful feature for our linear regression model to predict revenue. The spread also reminds us that while popularity is important, it's not the only factor affecting revenue. You can see there is a rough trend. Higher popularity often means higher revenue. However, popularity is not perfect, and there are surprises. This insight helps us select the right features. Feature selection and data preparation. For prediction, we need to pick columns that can help explain revenue. We will focus on budget and popularity as our features, which are numeric and easy to use. Our target variable, what we want to predict, is revenue. We prepare and split the data before building a model. Running the cell now. We will select only the columns we need for our machine learning model. Budget and popularity will be our input features X, and revenue will be our target Y. Create feature matrix X and target vector Y. X equals DF, budget, popularity. Y equals DF, revenue. Running the cell now. Here, we've extracted our features, budget and popularity, into the matrix X, and our target variable, revenue, into Y. This step sets up the data for modeling by clearly separating what we use to predict, features, from what we want to predict, target. Notice that choosing numeric columns simplifies later processing and ensures we focus on the most relevant predictors. X contains the data the model will use to make predictions. Y is what we want the model to predict for each movie. Splitting data into train and test sets is crucial in machine learning. The training set teaches the model, and the test set checks if it can predict new results correctly. We set test_size to 20% and fix random_state for repeatable results. Split the data for training and testing. From sklearn.model_selection import train_test_split. X_train, X_test, Y_train, Y_test equals train_test_split, X, Y, test_size equals 0.2, random_state equals 42. Print, train set size, X_train.shape. Print, test set size, X_test.shape. Running the cell now. This output shows the result of splitting our dataset into training and testing sets, where 80% of the data is used for training and 20% for testing. Notice the shape of each set, both have two columns, reflecting our selected features, budget and popularity. This step ensures we prepare our data properly to evaluate the model's ability to predict revenue on unseen data. You now have a separate set of movies for training and for testing how well the model predicts unseen data. Setting random_state ensures your results are the same each time you run this code, which helps with learning and sharing. Building the linear regression model. A model in data science is a way to mathematically describe patterns in data. Linear regression finds the line that best fits the relationship between inputs and the output. We will use sklearn to create and train a model. Running the cell now. We create a linear regression object and fit or train it on the training data. The model will learn the best combination of budget and popularity to predict revenue. Fit a linear regression model. From sklearn.linear_model import linear regression. Model equals linear regression. Model.fit, X_train, Y_train. Running the cell now. This output shows that the linear regression model from sklearn has been successfully created and fitted to our training data. It confirms the model is ready to predict the relationship between our input features and target values. This step is crucial for building a mathematical representation of the data pattern in the linear regression process. After fitting, the model is ready to make revenue predictions for new movies. Under the hood, the model works out the best formula to combine your features. A linear regression model uses an intercept and one weight or coefficient per feature. You can read these values to see how much the model relies on each feature. #check model coefficients. Print, intercept, model.intercept underscore. Print, coefficients, model.coef underscore. Running the cell now. This output shows the parameters of the trained linear regression model, the intercept and the coefficients. The intercept, -21,720,322.66, is the expected value of the target when all inputs are 0, while the coefficients, 2.20, 1,809,220.61, quantify how changes in each input feature influence the prediction. Understanding these values helps us interpret the model's equation and how it captures relationships in the data. The intercept represents what the predicted revenue would be if all features were 0. Each coefficient tells you how much revenue increases per unit increase in the feature, with all else held constant. Now we use our model to predict movie revenue for movies it has never seen. We print the first 5 true values and our model's predicted values side by side for a quick check. #predict on the test set. y_pred equals model.predict x_test. Print, first 5 true revenues, y_test.values, 5. Print, first 5 predicted revenues, y_pred, 5, .astype, int. Running the cell now. Here, we compare the first 5 actual revenues to the model's predicted values on the test data. Notice that while the predictions roughly follow the scale of true revenues, there are clear differences, highlighting that the model is capturing the pattern but with some errors. This step shows how well our linear regression model can generalize to new, unseen data. You can compare these numbers to see how close the predictions are. A good model will have predictions that are close to the true revenue numbers for most movies. To measure how well our model predicts, we use 2 common metrics. Mean squared error or MSE shows how far off predictions are on average. Lower is better. R² tells us how much of the variation in revenue the model can explain. 1 is perfect, and 0 means no skill. #evaluate performance using mean squared error and R². From sklern.metrics import mean_squared_error, R2_score. MSE equals mean_squared_error, y_test, y_pred. R2 equals R2_score, y_test, y_pred. Print, test set mean squared error, MSE. Print, test set R², R2. Running the cell now. The output shows the model's performance on the test set, with a very high mean squared error indicating large prediction errors, despite an R² of about 0.55 suggesting the model explains over half the variance in the target. This highlights the importance of evaluating multiple metrics. While R² suggests a moderate fit, the huge MSE warns that predictions may still be far off in scale. It's a key reminder to carefully assess model accuracy beyond just one metric when building regression models. You can use these 2 scores to compare different models and features. If R² is closer to 1, your model is capturing movie revenue patterns well. Plotting actual vs predicted revenue. Visualizing predictions helps us see if our model is making reasonable guesses. Ideally, the predicted and true values should lie close to a straight line. Running the cell now. Let us create a scatter plot where each point compares the true revenue with the prediction for a movie. The closer the points are to the dashed red line, the better our predictions are. #plot predicted versus actual test revenues. plt.figure, figsize sad smiley 75. plt.scatter, y_test, y_pred, alpha equals 0.4, color equals a purple. plt.xlabel, true revenue. plt.ilabel, predicted revenue. plt.title, actual vs predicted movie revenue. plt.plot, y_test.minute, y_test.max, y_test.minute, y_test.max, color equals a red, line style equals plt.show. Running the cell now. This scatter plot compares the true movie revenues, y_test, against the predicted revenues, y_pred, from our model. Notice how many points lie close to the red dashed line, which represents perfect predictions where predicted equals actual revenue. This indicates our model is making reasonably accurate estimates. Deviations from the line highlight where predictions are off, helping us visually assess the model's performance. If many points are close to the line, your model is doing well. Any big differences show where the model struggled, which could suggest more data or features are needed. Let us make this interactive. You can enter your own fictional movie budget and popularity score and see what the model predicts for the box office revenue. Try some values to see how sensitive predictions are to budget and popularity. Try predicting revenue for your own movie values. Budget equals float, input, enter the budget, e.g. 10 million. Popularity equals float, input, enter the popularity score, e.g. 10. Prediction equals model.predict, budget, popularity, 0. Print, predicted box office revenue, $int, prediction. Running the cell now. This output shows the predicted box office revenue for a movie with a given budget and popularity score, based on our trained model. Notice how the prediction aligns with the inputs, reflecting the model's ability to estimate revenue from these key features. This connects to our lesson by demonstrating how predictions can be generated for new data, which we later visualize to assess model accuracy. This simple exercise helps you see how machine learning can quickly estimate results for new cases. Keep in mind that the prediction is based only on the simple features and the data we use to train. Practice challenge. Can you add a new feature to improve prediction? Try using runtime or vote_average as an additional column in X. Retrain the model and compare the R² score. Small experiments like this help you learn fast and build stronger skills. Running the cell now. What you learned. You explored, cleaned, and visualized a real-world movie dataset. You built and tested a simple model to predict box office revenue. You learned the basics of linear regression, model scores, and feature selection. These skills are the foundation for more advanced data mining and modeling. If you enjoyed this, please subscribe to our YouTube channel for more beginner-friendly data science lessons. Running the cell now. Where to go next? Try different models like decision trees or random forest. Add more features or clean data differently to explore data science more deeply. Watch our next video to learn about classification, clustering, or recommendation systems. Running the cell now.